Let us see how dynamic programming can be used to solve the rod cutting problem, that is to find an optimal rod cutting. Here is a subproblem tree for the rod cutting problem for a rod of length equals 4. If you remember, we know that solving the optimal revenue for a rod of length 4 involves solving for length 3, 2, 1, and further 3 needs to be solved for a rod of length 2, 1, 0, and so on. The key idea behind applying dynamic programming to the rod cutting problem is we arrange the subproblems in such a way that we only solve one subproblem just once. So in this case, here's one subproblem to solve a rod of length 2. Here's the same subproblem that is being solved twice. So the idea is we want to update our code or change our algorithm such that these two solved problems are only solved once only. That is exactly what we would like to do with dynamic programming. Now, during computation, say for example, we are trying to calculate the optimal revenue for a rod of length 4, and then we happen to solve this. So if this for R2 is solved, then what we would like to do is during computation, when we are calculating other things, we simply want to look this solution up, look it up, and use a already solved solution instead of recomputing it. So that's the core idea behind how we can apply dynamic programming to solve the rod cutting problem. Now, there are two approaches to implement or to design our dynamic programming solution. One is the top-down approach. So this is the same approach as the recursive approach, where we start by trying to solve the problem for a large value of L. In this case, we want to solve for R4. Then we length equals to 4, and then we break it down to L3, L2, and so on, and then we further break it down. So this design is similar to the recursive design, so recursive design, but then we simply want to attach the idea of dynamic programming, that is memoization. In other words, just memorizing what the already solved solutions are. The next approach is to just the opposite, that is the bottom up approach, where we, instead of solving directly for L equals to 4, we start with a solution that starts by solving for equals to 0 first, and then 1, 2, 3, and so on. So in other words, just opposite to the way a recursive solution would solve it. So here's the top-down dynamic programming approach to solve the rod cutting problem. So this is simply an improved version of the recursive solution. We also call this the memoized rod cutting algorithm. Now you might notice that this is not memorized, but it is memoized. But we could say that memoized basically refers to memorizing the solution in a table so that we could use the solution as needed. So to simply add this memoization to the recursive algorithm, all that we do is add initialization code to initialize this table for um, to maintain the solutions for a various length. So if this is my length and this is my optimal solution, or in this case, revenue, we can initialize this to be a very large negative number, saying that this is unsolved. So what I do is create an array called R, which I initialize to minus infinite for every element. And then this is where the main program starts happening by taking Pn, which we earlier had in the recursive solution, but now we also pass um, R, an array that maintains the best known solutions for subproblems so far. So the rest is all same, just like the standard recursive rod cut algorithm. The algorithm takes Pn. Now it additionally takes this pre-solved table of solutions, and then we simply check if the table already has the solution. If the solution is there, we don't do anything else and we simply return the solution. Otherwise, everything else is same. So we once again check it, initialize the revenue to some very large negative number, and then we try to cut every possible place at 1, 2, 3, 4, and so on, and then recursively caught the rod cut algorithm again. Now, one additional difference at the end is once we have found a solution, what we want to do is maintain the solution in a table, right? So that this table contains solutions that further will not be resolved again. Now, this table R that contains solution must be passed by reference so that subsequent function calls keep changing the same table. Now, if we compare the recursive top-down approach versus the dynamic programming top-down approach, that is the memoized recursive solution, you will see that the only difference is that before trying to solve the rod cut problem for a length of n, we check if the solution already exists in a table. Is it already exists in a table, right? This is checking, and then if it doesn't, we update the table. So this is where we update the table. Otherwise, these two solutions are basically the same.
Now, to solve the rod cutting problem, instead of going top down, that is trying to solve the largest length rod first and then going down to solve the smaller length, we can actually do the opposite, that is go bottom up. In other words, we first try to solve the problem for a rod of a very small length and then gradually grow up. This is exactly what the bottom up rod cutting algorithm does. So once again, we initialize or we create an array called R where we want to maintain our solution for a rod of all the lengths up to n, right? So for R equals 1, 2, n equals 1, 2, 3, all the way to n, we want to maintain a table with all the corresponding solutions. Now we initialize that for a rod of length 0, the revenue will be 0. And then we run the loop to calculate the revenue for a rod of all the lengths from 1 all the way to n. So first we calculate the revenue for a rod of length 1. Then in the second time, for when j equals 2, we calculate the revenue for the rod of length 2. And here, this assignment updates the table each time. So once we have solved for j equals 1, we update the table and we say that we have calculated the revenue for the rod of length 1 and so on. And the inner for loop here, since we have double for loop, what the inner for loop does is it looks for all the possible ways to cut the rod. That is, for a rod of length, let's say 4, we want to go from I1 to J. That is, we want to cut at the first place, second place, third place, and so on. So every time we make a cut, we notice that we don't need to call the rod cutting algorithm again. What we simply do is look up this table and pull the value down from the table. Now, since we are solving a subproblem I, that is always here, this the subproblem I that we have inside is always smaller than the subproblem J that we are trying to solve. We will always find that our this table Rj minus I has a solution that we're looking for. So in this way, we calculate the optimal revenue for a rod of length 1, then we calculate for 0, then we calculate for 1, and then for 2, and then for 3, and then for 4 in a bottom-up fashion. So this is how the bottom-up rod cutting algorithm works.
Now, to briefly compare the two different approaches of dynamic programming, the first one is the memoization approach, that is improvisation of the recursive approach, and the next one is the bottom-up approach. What we see is that both of them have a similar asymptotic running time of around big theta n square. Now it's n square because if you look at the recursion tree for the memoized rod cut, that will also be evident. But for the bottom-up approach, we see that we have a double for loop, right? So the first for loop goes from 1 to n, second goes from 1 to j. So this becomes like the number of times the inner for loop runs is like an arithmetic series, 1 plus 2 plus 3, da, da, da. Essentially, if we sum the total number of calculations that the algorithm has to do, it will eventually turn out to be in the order of big theta of n square. Now, even though for some people the recursive algorithm might sound intuitive, recursion is something that is not encouraged in many applications for many reasons. And also it turns out that the bottom-up approach actually slightly outperforms the top-down approach by a constant factor, probably because it doesn't need to initialize a stack and all those things. So typically, the bottom-up version with the double for loop type implementations are usually preferred. Now, the dynamic programming solutions that we looked so far only give us the optimal revenue, maximum revenue, Rj for a rod of length j. But we know that the solution that we need to generate is not just the revenue, Ri, but also the answer to where to cut the first piece off. So for an input table like this, which is our problem, right? Problem, our solution should look something like this, where this I is the length of the rod, and then what we have Ri is the optimal revenue that we're going to make with that given rod length, and Si is the first place where we should cut the rod. Here's an example. If I have a rod of length 4, the maximum revenue I can make is $10, and the first place I should cut the rod is at after 2. So if I have a rod of length 4, if I cut it at 2, then that is the optimal cut I can make to make the most amount of the highest revenue, and the maximum revenue I can make is $10. So the solution that we saw so far only give us these numbers, that is the maximum revenue. They don't give us the optimal place to make the first cut. Returning such a solution is not extremely difficult. Say, for example, if we are talking about the bottom-up solution, then all we need to do is change the max to this if condition, so that max goes to if condition, so that any time we observe an improvement, we notice that, we make a note of where we actually had the case of better revenue, and then save it into an array Sj. Now this array Sj or Sn maintains the list of indices to make the optimal cut. Now, when applying dynamic programming to a problem, we should understand primarily the set of subproblems involved. That is, how many unique subproblems do I have in my problem that need to be solved? Essentially, what we want to do is sort of get an intuition or understanding of how big this table may look like. Also, what we want to understand is how do the subproblems depend on each other? And the best way to represent these two information, that is how big the subproblems are, how many subproblems we have, and how they depend on each other. One really good way to visualize this is using something known as subproblem graphs. And here's an example of a subproblem graph for the rod cutting problem with a rod of length L equals 4. So you can see that to solve a rod of length 4, we need to have a solution for a rod of length 3 represented by this arrow, rod of length 2, rod of length 1, and rod of length 0. Similarly, to solve a rod of length 3, it depends on the solution to the rod of length 2, 1, and 0, and so on. So this is more or less like a reduced or collapsed version of the recursion tree, where it is much more clear how many unique subproblems we have and how the subproblems depend on each other.